Welcome back to ECE 320A. Now that we've learned a little bit about three-phase systems, the wirings of sources and the wirings of loads could be either delta or Y. We also have to understand positive phase sequences and negative phase sequences, and that those have to be consistent throughout a system. What we want to do now is talk about how we can find the complex power of a load, and that load you need to be clear as to what somebody is asking. Is it a particular phase that they want the complex power, or is it the total of all three phases? And we'll compute the A phase complex power of a load, and then if our system is balanced, that the total load power, I should say total complex load power, or maybe I should put that total load complex power, will be 3 times any of the individual phase powers. And we will look at computing the complex power of the A phase for a Y-connected load and a delta-connected load, and hopefully it will be clear what we're doing. But in both cases, we have to worry about keeping track of the A phase voltage and the A phase current at the load. And those can be different depending on what kind of wiring we have at the load, whether that's a Y-connected load or a delta-connected load. Here is our YY configuration that we've introduced before. And what we are working with now will be the A phase to try to find the complex power of the A phase of the load. Now, if I said find the complex power, I hope that you're starting to immediately recall or be able to write down an expression for complex power. And if you were in an interview and somebody said, oh, what's the complex power of the A phase? And you go, oh, it's been a few semesters since I've had 320. Let's see, it was power is voltage times current. It seems like there was, oh yeah, we had to worry about the conjugate. It was VI conjugate. But now it's more important, it's equally important. So, okay, you get partial credit for finding V times I star, but now we want to find the A phase's complex power, and V means what? I means what? These are obviously phasors, so we have to make sure that they're phasors, but now we want to find the A phase's complex power, and really what we're doing is we want to know what's the power absorbed, or I guess if you had a weird load, supplied by that impedance in the A phase. So we're looking at the A phase impedance and finding the voltages across that impedance and the current through that impedance. And in this case, I hope you can see that although it's drawn over here, this A phase current in the transmission line is going into the positive terminal of the A phase impedance. And so our current in the A phase in this expression will actually be I sub AA. That's the current that passes through that impedance in the A phase. And what's the voltage? Well, the voltage dropped across that impedance is not in red, V sub AB. That's the transmission line voltage drop between terminals A and B. But the A phase voltage across the A phase impedance is actually capital V sub AN. So in this equation, to find the complex power of the A phase of our load, we need to find the phase voltage, which we just found. So here is our phase voltage. Again, this is for a Y-connected load. That's V sub AN. And we need to multiply that by the complex conjugate of our phase current. And these are both A phase current and A phase voltage. The phase current is the current through Z sub A. The A phase voltage is the voltage drop across Z sub A. That's the phase voltage. And you could also say that this is, in this particular interconnection structure, this A phase current is actually the A phase line current. So this is the line current in a Y connected load. And I hope that you can see that V sub AN, which is the phase voltage in this Y connected load, that's not the same as this voltage drop VAB. I don't want to emphasize that too much, so I'm going to erase that, but I hope you saw what I was referring to. So in this particular Y configuration, the phase voltage of the A phase of our load is not the same as the line to line voltage from transmission line terminal capital A to transmission line terminal capital B. And a lot of times this will simply be abbreviated as the line voltage. In the Y connected load, the line voltage is not equal to the phase voltage. And I hope that you can see that VAB, in this particular case, that phasor, is not equal to V sub AN, because V sub AN also has to be combined with V sub BN in order to get us the line-to-line voltage of the A phase, which is V sub AB, with A being the positive terminal in that measurement. There is now our expression for the complex power of the A phase of our load. And if you now can find V sub AN, the phase voltage in the A phase, and if you can find I sub AA, the phase current, or the line current in this case because of its Y connection, then you take the voltage phasor times the complex conjugate of the current phasor, and that produces the complex power of the A phase of that three-phase load. And you do the same thing for the B phase. The B phase would be utilizing the phase voltage of the B phase, V sub Bn, and the phase current of the B phase, and likewise for the C phase, if you needed to calculate all of those. What rescues us maybe, if we were computing this total load power, the total load power, that needs to incorporate all three phases. So the total complex load power, or the total load complex power, sometimes I get a little bit lazy and don't say complex, but the total load complex power is the sum of the three individual phases. Now, if we're in a balanced scenario, then all three of those load phases, A phase, B phase, and C phase will have exactly the same complex power. And that's why I said this can minimize our work. If it's balanced, we simply need to compute the complex power of one of the phases and then triple it, and that will give us the total complex power of the load. That's for a Y-connected load. What happens if we now have a delta-connected load? Here is our delta-connected load, and it's a little bit big, I guess, in terms of fitting on the screen. I guess I could try to reduce that a little bit. So here is now our delta-connected load. And what do we do? Well, if somebody says, what's the complex power of the A phase, what will that be? Well, the A phase load power is going to be the current going through the A phase impedance, which in this case is I sub AB. And look, it's going through the positive terminal of the A phase load impedance voltage V sub AB. So now we take the phase voltage and the phase current in this complex power expression. It's just now those are different because we're in a different wiring configuration. Now we're in the delta configured wiring strategy. And what do we have? Now our phase current in the A phase is not I sub AA, because that now gets divided among I sub AB and I sub CA. I sub CA is coming in, and all of those are going to then be algebraically by KCL determined at terminal A. So to find the complex power in a delta configured load, we need to concentrate on the phase voltage and the phase current. And in this case, the phase voltage is this line-to-line voltage because it's a delta connected load, and our phase current is the current that's passing through that particular A phase impedance. So in our case, we now have the A phase load power is V sub AB phasor times I sub AB phasor. And this is now the A phase load current, or the A phase current, and that's not equal to the A phase line current, which is I sub AA. What is V sub AB? Well, V sub AB is actually the A phase load voltage, which in this case is equal to the A phase line voltage at the load. Because we could have the line voltage at the terminals of the source or the line voltage at the terminals of the load, and that's why I put this at the load distinguishing comment. And here, I hope it's clear that this A phase line current, because we're in a delta connection for our load, is not equal to the A phase load current. So the A phase load current in this delta connection is not the same as the A phase line current, contrast that with now the A phase load voltage is in fact equal to the A phase line voltage. And again, if somebody wants the total power, complex power of our load, we simply add up those three pieces. Complex power of the A phase, complex power of the B phase, and complex power of the C phase. And if it's balanced, then we just have to compute one of those, A, B, or C phases, and triple it, and we have the complex power total of the three phases of our load. Now, I hope you can sort of see that it might be helpful to understand or use conversions between delta to Y and Y to delta, either at the loads or at the sources. And just to give you some formulas or equations to keep track of for impedances, you can find those either for sinusoidal steady state in section 9.6 of the textbook, or for the classical resistor case back in chapter 3, section 7, you can see the equations for converting impedances or resistors. And in equation-wise, if you want to now, if you had a set of impedances that were connected in a delta configuration, and maybe for ease of analysis, you want to convert those into a Y interconnected structure, then you would use equations 51 through 53 in chapter 9. If you were presented with a Y connected set of impedances and you wanted to go to a delta interconnection of impedances, then you would use the next three equations, equations 54 through 56 in chapter 9. And we will probably go through, but you can now apply that impedance conversion to the sources if you have source impedances that are connected either in delta or Y and you want to go the other direction. And we'll start to connect or relate or show how to convert voltages from deltas to Ys, which, for example, in a Y connected configuration, I think you can see that the phase voltage is not the same as the line voltage. And so we will work out the relationships between line voltages and phase voltages in these different configurations. Likewise, we can also find relationships for phase currents and line currents, which for this delta connection are different. So in the delta connections, we might be interested in converting or knowing the relationship between phase currents and line currents, and in Y configurations, it might be helpful to know the relationship or connection between phase voltages and line voltages, and we'll derive those relationships for balanced configurations.